Greetings and salutations, pre-calculites. We are actually starting the pre-calculus. So we've been doing an Algebra 2 review for the last for the last week or so, and we're going to be starting with the beginning of the book, and this is what the book looks like. All this information that I'm giving you can be found on pages 1 to 9. All algebra classes start with talking about real numbers and how to categorize them, converting between decimals and fractions, and so on. So today what we're going to be doing is talk about representing real numbers, order and interval notation. That may or may not be new to you, but we'll explain how to go about that and give you some examples. Basic properties of algebra, which you should already be familiar with. Integer exponents and their properties, which you should already be familiar with, and scientific notation, just a quick refresher on that. These topics are fundamental in the studies of mathematics and science, so you need to know all about them. First off, the first part of your homework says to convert something to a decimal. So if you have a fraction like 2/5, just recall that 2 divided by 5, that's what this stands for. So 2 goes on the inside and 5 goes on the outside. So if you're doing this longhand, this is how you would represent 2/5 as a division problem. Since 5 can't divide into 2, you have to add a decimal point and a 0, and then you take and put your decimal point up on the fraction bar and say 5 into 20 goes 4 times. So you end up with 0.4. 4 times 5 is 20. Subtract that off, that's a remainder of 0. So this is the decimal form of this fraction. This fraction is called also a ratio. So when they say rational numbers, that's what they're getting at. Since our decimal ends, it's called a terminating decimal. So we would say 2/5 is the same as 4/10 or 0.4, and it terminates. Something that wouldn't terminate would be, for example, a fraction like 2/9. You can plug that into your calculator, 2 divided by 9, and your calculator will give you 0.2222222. That's called a repeating decimal, and you put a line over the digits that repeat. The part that repeats, just to refresh your memory, is called a repetend. All right, let's move on. What is a real number? It's any number that can be written as a decimal. Whether it would take you forever to write the decimal or not, that's what a real number is. Natural or counting, they start at 1 and go up by ones. 1, 2, 3, 4. First numbers you learned. Whole numbers add zeros to the natural numbers, and the integer set has all the -1, -2, -3, and so on. So rational numbers are those 3 sets of numbers. They're rational numbers because you can put them over 1, but they're any number that can be expressed as an integer over another integer. So this set notation is a more advanced notation. This is a over b such that, that's what this vertical line means, a and b are both integers, and b can't be 0 because that would make the denominator 0, and that would make that undefined. The decimal form of a rational number either terminates or is repeating forever, indefinitely repeating. Irrational. No, don't say that's your girlfriend. Irrational is a number that's not rational. So the decimal is infinite and it doesn't repeat in a pattern. So let me just give you this. I gave this to my Algebra 2 class, but if you wanted to look at this visually, you'd have, let's say this big yellow egg is a set of real numbers. It's split into 2 different parts, the irrational numbers and the rational numbers. I do the irrational ones first because, not that they're smaller set, but there's more inside, there's more categories inside the rational numbers. But irrational numbers are any number that you can't express as a fraction. So that means a decimal doesn't end or repeat in a pattern. And they're numbers such as the square root of 5, negative square root of 5, negative square root of 3, square root of 3, square root of 2. Pi is an irrational number, which is interesting because pi started out as the ratio of the circumference to the circumference over the diameter, which, it started as a ratio of 2 things. Anyway, ironic. But rational numbers can be expressed as a fraction. The decimal is going to terminate or repeat in a pattern. So ones like 1/2, 3/4, -1/7 are all rational numbers. Inside the set of rational numbers, you've got your integers, your natural numbers, and your whole numbers. Whole numbers and natural numbers. This is a pictorial of how the sets are interrelated. If it's a natural number, it's a whole number and an integer and a rational number and a real number. You ask, what numbers are not real? those are going to be the imaginary numbers. Square root of -1, imaginary. And you might have seen that in Algebra 2. But that's what's a number that is not real, is an example of a number that's not real. You should be familiar with the real number line. It expresses all the set of real numbers. It goes into opposite directions. Remember, negative is to the left and positive is to the right of 0. As you get further left, it's smaller. As you get further to the right, the numbers get larger. And you can put a dot anywhere there's a number. So like pi, you know it's a little over 3. They put a dot there to represent pi. Ordering real numbers, you can say it's greater than, less than, greater than or equal to, less than or equal to. You should be aware with that of what that is. And trichotomy property says either a number is less than, equal to, or greater than another number. Bounded intervals. Now this is where they start with the interval notation, which you may or may not be familiar with. But if you look at this one, it looks like an ordered pair, which is why they did not introduce this to you prior. They didn't want you to get confused with it. This interval notation, this is the same as saying x is between these two numbers. X is between the numbers a and b. They include a and b in the graph. You may have been familiar with the circles, the open dot and the closed dot. Let's say I had a number between 5 and 8. I read this as all numbers between 5 and 8. Doesn't include the 5 and it doesn't include the 8 because there's not an equal to symbol. So I put an open circle at 5, an open circle at 8, and I'd shade in between there. Well, instead of the open circle, they're going to have you use these parentheses. So they're going to, and this one actually is wrong. Your book picture is wrong. I hope that's not wrong in your book. This should be a round parenthesis here and here. So it should look like this. And notice how the parentheses face each other, kind of to tell you it's all that in between there. And the interval notation is 5, 8. All these things mean the same thing. So you can write it like this. You can do the open circle and shade between. You can do this and shade between. You can do this in this notation, and that is the interval notation. And as you practice it, it's very simple, especially if you know your open and closed dots. Those were called closed intervals because you had endpoints. These are called open intervals because they go off forever. So for example, you want all numbers bigger than a, let's say all numbers bigger than 3, bigger than or equal to 3, it goes off forever to infinity. And whenever they have the infinity, they've got the rounded parenthesis there. All right, so this is called an open interval because it goes forever somewhere. Writing that, we would use the squares. That's going to be like our closed dots whenever we see the less than or equal to, and your parentheses are like the open dots, and that's when they use less than or greater than. So this is number 3 down here. I want to do a couple other examples before we get to that. So example 2, this is all numbers that are greater than 2. One little trick is if your variable's on the left, the inequality points the direction you're supposed to shade. So if we're looking at this guy, I do my number line, just draw it out. I can put 0 anywhere. I label where the 2 would go. I used to put an open circle and I'd shade all the numbers bigger than that, so to the right. Now I'm going to use a parenthesis. And since we're shading to the right, it cups around where that shading is going to be. And our interval notation would be 2 to infinity with those round parentheses. X less than or equal to -8 means all numbers smaller than or equal to -8. So if I draw my number line, I normally would have put a closed dot and shaded to the left. But now, instead of the closed dot, we're going to use the square bracket. And we're going to use the square bracket so it kind of points the direction we're shading. It goes down to -infinity, so I put -infinity first, and then -8 and a square bracket around the 8. All numbers between 3 and 5, closed dot would go on the -3 and open dot on the 5. And we'd shade between. Well, instead of the dots, we're going to be using these parentheses. Square parentheses going to go in place of the closed dot, and open parentheses going to go in place of the open circle. So this is what this would look like, and in an interval notation, we just bring it down, the square bracket, -3, round bracket, and 5. Hopefully that helps you with the interval notation. If not, I'll be happy to explain it to you in class. Properties of algebra, changing the order of addition or multiplication is totally legit. Associative property, that's changing the grouping symbols. Identity properties is something that when you add or multiply this to the number, it keeps its identity. So u plus 0 is u times 1 is u. Inverse property, you've got your additive inverse, which is the opposite. You've got your multiplicative inverse. Distributive property, you should be aware that you can multiply the number if it's to the left of the parentheses or to the right. You can distribute that through the parentheses. Multiplication over subtraction, same thing. Additive inverses. Two negatives make a positive. Opposite of a negative is a positive. And then with one negative, it doesn't matter where you put the negative when you're multiplying. These two cancel out for a positive, and I think you guys are pretty familiar with that. They give some examples in the book with numbers to help explain that. Exponent, the definition. If you have a to the n power, a is called the base, n is the number of factors. So you've got all these a's, there's n of them. And this we've already covered. Here's properties of exponents, which you should be familiar with when you add, subtract, multiply, and divide. So you're going to get some more practice with that, but this time they won't be fractions. But if you can do the fraction ones, you're going to do great on these. So let's do an example of simplifying these expressions with powers. Remember I told you the negative exponents, they just change the location in the fraction. So if it's in a fraction, if it's on the top, you're going to move it down, and if it's on the bottom, you're going to move it up. So I just rewrote this so you can see what we're going to be doing. So this a to the negative 1, he comes up and subtract exponents. If you look at your properties, you subtract exponents of the same on the same basis. So you'd have 2 minus a negative 1. And down here the v would move downstairs because he's negative, so to make him positive it'd be minus a negative 3 down below. So you'd end up with u cubed over v to the 5th. That's about the most complicated one you're going to see. Scientific notation. Oh yeah, this is something that you should dig. The only two things you have to worry about with scientific notation is this number right here has to be between 1 and 10. They like to put that on standardized tests where that number is not between 1 and 10, so it's not officially in scientific notation. Also, m has to be an integer. It can be positive or negative, but it has to be an integer, no fractions. If the number is small, your exponent's going to be negative. So if you have something like 0.0000000000000000587, then when you multiply, the power on the 10 here is going to be a negative. The exponent reflects the number of spaces you move the decimal from your original number. So let's do an example. If I'm converting this to scientific notation, first off, I see it's a very small number. So in my brain, I go, okay, it's going to be 10 to the negative power. This is where I would put my decimal point because 3.45 is between 1 and 10. And I would move it 1, 2, 3, 4, 5 spaces. So this would be 3.45 times 10 to the negative 5th power. That's it. I think you can handle that. If you're converting from scientific notation, I notice the number is positive. That's going to be a big number. I'm going to move my decimal 5 spaces to the right. So I take my 1.323 and I move it 5 spaces to the right. If I end up with blank spaces, I put some zeros in there, and bada boom, bada bing, you're done. 123,000. That's it. So I hope that you guys are going to be ready to hit the first section of homework tomorrow, and I will see you then.